right. Hi, everyone. This is Kerim Baran with Solar Academy. And today I have a very exciting, unique new technology that a team that has been working on quantum photonics related research, deep research and deep science that is bringing a new technology for solar asset maintenance, O&M, and further information about the performance of these assets. And the team I have are two Saudi brothers, Omar and Osman. I got to meet recently, and their teammate Dilsher, an ex-Googler. They are based in the Bay Area and Saudi Arabia, and they have been working on what we call the $1 trillion blind spot in solar, as solar assets are now approaching north of what is that, 3 gigawatts probably now, 2 to 3 thousand gigawatts, sorry, globally, which equates to about $2 to 3 trillion of energy assets, a huge category, as folks in the solar industry and familiar with solar industry has observed grown probably 20x in the last 15 years. The maintenance of these assets are becoming a major problem, and most data shows that these assets usually underperform 5 to 10% of their original predictions. And there's all sorts of reasons for this. One of the most important one is the micro cracks in panels and many other issues, obviously. And we're going to talk some of these and how the research and the quantum I'll let the science be explained by Omar and Osman. So, Omar, maybe I give you the stage for a few minutes just to talk a little bit about your background, and then Osman and Dilshar, if you can do the same for a few minutes, and then we dive into Q.Fly, your main product that solves this problem. So, Omar.
So thank you, Karim. It's a pleasure being here with you today. So just to give you a quick on my background, I'm basically an entrepreneur and investor in Silicon Valley. I've been in tech for almost 30 years. First, as an academic, I did my undergrad and bachelor's at MIT and my PhD at Berkeley, all in electrical engineering and computer science. And then I started my first company, Toronto Wireless, in high-tech broadband-based technology, building fiber alternative gigabit delivery mechanisms with wireless.
And that was a $1 billion exit, if I remember correctly, right?
Well, it's $1 billion+ company today, but it's
right.
Not yet an exit. Okay,
Okay.
we're still a private company.
Okay. Right.
But we're doing very well and expanding rapidly in the U.S. and we're going to start growing internationally pretty soon.
Yeah.
There. And since then, I've also got involved or started several other ventures. The biggest of which is this company, Quantum Solutions, which I'm working with my brother right now to make it the next multi-billion-dollar company.
Right. And Osman, maybe we can hear a little bit about your background and credentials and research, and I believe you have a PhD also in related areas. If you can touch on that a little bit.
Thank you, Karim. It's a pleasure and an honor to be on your show. And my name is Osman Bakr. I'm the founder of Quantum Solutions, which makes the Q.Fly solar system. And I started my career as and I still am a professor of material science and engineering and applied physics. I earned my undergraduate in material science and engineering at MIT, and then I did my PhD in applied physics from Harvard. And then I started did a bit of some more work on quantum optics before starting my faculty career and my research at KAUST, Saudi Arabia. And I spent a lot of time, I spent my career studying how atoms interact with light, specifically, especially light that our eyes can't see, and how can that interaction be used to detect light that our eyes can't see. And so quantum solutions is a result of many years of research in developing materials and that called quantum dots that we use to detect light beyond the perception of our eyes, and beyond visual perception, and how we turn them into sensors, and then eventually into entire systems, imaging systems that are end-to-end turnkey solutions for our customers to solve really billion-dollar problems in the solar industry and the water industry as well.
And Dilsher, would love to hear about your background as well, because you complement.
Absolutely. Thank you, Kerim, very much for the invitation. My name is Dilsher Ahmed. Uh, uh, I'm in a room where I definitely feel very undereducated right now because I'm only a master's, not a PhD at all. So I did my bachelor's from Carnegie Mellon and then my master's from Stanford, in both in computer science, primarily focusing on databases. Moved over to work at Google for about 5 years, working on a variety of different products, including Android messages, YouTube, etc. Worked on YouTube Shorts, so part of the reason the modern world now has very short attention spans. And then moved into the startup world after that, and worked on a variety of different startups with different clients, including Department of Homeland Security and a lot of secure products, but also just generally a variety of different spaces. And then a few years ago, started working with uh, Quantum Solutions on AI solutions for the solar and water products that we're developing, and in general, been learning more and more about the different challenges of image processing, signal processing for solar, working with a fantastic team that I've known for several years from Carnegie Mellon, who are part of our AI team, and just generally trying to make sure that we can create a great solution that works for end customers and keeps the spirit of communication open to end customers in the sense of not being too technical and digesting that technical information for our end customers.
Great. Thank you. Thank you very much, guys, for this background. So today's conversation will explore your new approach to essentially with your deep tech and scientific approach of using shortwave infrared imaging to identify issues with solar assets. I guess that is what we're going to talk about. So as we dive into this conversation, can you tell us a little bit about the science behind your innovation, Osman? Tell us a little bit about the science of invisible light and what that means in the context of solar and solar assets.
Thank you, Kerim. So, Kerim, when you mentioned shortwave infrared, and that's the spectrum of light that's closest to visible light, yet our eyes cannot see. But it's actually quite a wide range of spectrum. It goes from 900 nanometers all the way to 2,500 nanometers. And it's a spectrum where rich phenomena happen. Materials look different depending on the specific wavelength of light that you use to image them. Water, gases interact in a very different way than what we see in visible light, and from that, in those interactions, we can deduce many information and valuable data about the quality of the material, the state of the structure that we're investigating. It tells us a lot of information that our eyes can't see. The information basically that very important, that precedes the damage that our eyes can see. And so this is where we started finding this spectrum very interesting. And the way we started working on that in that field, we started in a class of materials called quantum dots, and these are materials that are semiconducting nanocrystals. There are a few hundred atoms, and by controlling their precise size, we can control how their electrons can absorb light, and by dialing their size, we could make them absorb specific wavelengths of light. And so we were able to make quantum dots that absorb very specific wavelengths of the shortwave infrared, wavelengths that we could dial on demand, design on demand. And what we developed ways of integrating them into sensors, to make sensors that detect the desired wavelength of light, and turning it into a signal. And so what we've realized is that there's quite a number of spectra of light that could be very useful in inspecting solar energy infrastructure, as well as in remote sensing. And so we designed our technology to do that. We spent many years developing the materials and the sensors, and then we also realized that because the data that gets collected by these sensors is so rich, it's not just it's not just what we see in our visible with our visible eye. When we see a change in the scene, can be things that change, but also colors that change, materials that change, and these phenomena manifest differently in shortwave infrared compared to what our eyes can see. And so that required a lot of complex and computation, and in order for the user to be able to make a decision for what's happening. And so we realized that we had to combine this with a platform that's easy for the user to use and easy for the user to interpret. And that's why we spent many years integrating these sensors with drones, and then eventually even creating the full stack AI stack, so that we can the end user doesn't need a PhD degree to interpret what's going on, and will get actionable data in a very simple format without the need to resort to experts. So we spent many years going from atoms all the way to actionable insights with AI. That's all.
Got it. So you guys kind of provide
Exactly.
an application platform for these asset managers to use, and identify issues and see suggested actions, and
Exactly.
then trigger those. Got it. And so,
Yeah.
I mean,
Yeah. And
I've been in the industry for 16 years now, in solar industry, and the amount of knowledge I had about imaging and using drones to inspect solar panels and assets and performance is to the extent of thermal imaging. I think that's something that is the prevalent way of doing these asset inspections and main O&M activity. So what's the advantage that your technology brings on top of that? Can we talk a little bit about
thank you. So
what's the
yeah,
difference?
yeah, I'm glad you asked that question. So what we realized, and that's been known in the industry, but there was no really good solution around it, that thermal and visual inspection miss almost 80% of the damage that occurs on the cell level. And so thermal is kind of a secondary indicator. It's like it looks at the hotspot, but doesn't if the underlying damage generates a hotspot, but doesn't tell you what that damage is. And often that damage occurs without generating a hotspot. If I had to put an analogy, thermal is like a thermometer, and tells you have a fever, but it doesn't tell you where that fever is coming from. But oftentimes you don't, you could have you're a symptom of an early disease that doesn't manifest. You know, can't, you know, you can be having cancer and there's no fever. You know, that's
Right.
so. And we found that we realized that thermal really misses out a lot, and not only that, it actually, by the time you start seeing things in thermal, it's already too late. You know, it's already, the damage is already there. And so what we looked at a technology that's been around. It's called electroluminescence, and that's been a technology that's been kind of the gold standard in studying and looking at what's happening at the panel level, because it actually shows not just, you know, the temperature change. It shows that actually you could see how the electrons are flowing in the cell, essentially. So it tells you the cracks. It shows you the whether potentially induced degradation and other soldering faults, any fault that can lead to any electrical anomaly appears, and so it's very sensitive. The only problem is, we realize in this is that it required very sophisticated and equipment. So many of the folks in the industry would either have to, in order to do to it was a very expensive process. You either had to unrack the panel and send it to a lab for it to be inspected, or you showed up at midnight in the solar facility with a handheld camera, and you spend 10 minutes looking at hoping your camera is sensitive enough to capture the electroluminescence that comes out. So you can imagine how really prohibitive that is. If you mentioned there's there now we have terawatts of thousands of gigawatts
Gigawatts of
installed already.
assets.
Well, yeah, worldwide. Even a single gigawatt is a couple of million panels, and nowadays it's very common to see plants that are hundreds of thousands to millions of panels, and so it was absolutely impractical to actually use this technology, and so and you only use it as the last resort on 0.001% of your panels. And so what we realized is that we could emulate that technology by using the materials and sensors we developed, and we could put them on a drone. And so instead of unracking the panels, you can scan them. You can scan them on while they're in the field, and moreover, because our technology is so sensitive, and we spent a lot of time on the data processing and image processing, we were able to do it day and night. You could do that day and night without disrupting any of the operations of your facility. And so we took a process that you need to spend an hour on to do, and a lot of labor, to a process where it took literally a couple of seconds. And so then you can as
And the hour that you are referring to, is that the hour in the that it would take with thermal imaging in the somewhere else, or
no. So a typical work, there are many but a typical workflow would, people would send their thermal imaging throughout the facilities, their panel, and maybe if they detect an anomaly, they take one or two panels and they send them to the lab.
Yeah,
and
I would think that takes more than an hour.
Yeah, it would take it takes hours. I mean, it takes hours. It's not just sending it to the lab, but also having someone interpret it and say what we're looking at, and then you're looking only at a fraction of what you have, and often actually the panels you see through thermal, like, they have to be very bad in order to see like appreciable thermal effects. And so, yeah, in fact, it was just it took, I'm being generous here, I'm conservative, just saying it took
Yeah.
many hours. And so it took many hours to collect and many hours to interpret, and then many hours. God knows how many hours to make the claims and to actually do something about it.
Right.
And as you know, nowadays, actually, the biggest cost in this industry is actually labor.
Right.
So imagine, you wouldn't want to send someone out there to take out a panel somewhere in the middle of a field that's a mile, square miles, to pick out a panel and then take it out, unless you knew for certain there's an issue that deserved uh, your uh, your attention. And what we strive to do is not just to create a system that that does what you do, what basically a flying lab. It also tells the user, gives the user a score for the damage, that classifies the damage, a score. Is it worth your time to go there and right now, or should you wait for a scheduled maintenance, or should you not care at all? I mean, is it even worth your time?
Right. So, and what are the reasons all of this is? I mean, I guess you want to identify these issues at the panel level, at the string level, at a solar plant level, statistically, I'm assuming, to make insurance claims, to get warranty replacements from manufacturers. There might be some other
Yeah.
reasons as well. And so I am assuming your data set is being used to justify these actions. Is that
Yeah.
a fair way
That's
to
fair. That's
describe it?
actually, yeah. What we're finding is many parts of the ecosystem, many players in the ecosystem are finding this technology quite useful. So as you
Okay.
alluded to, the most obvious ones are the warranty, and now as the number of panels is proliferating exponentially, there's no way to start, kind of getting a handle on the kind of damage you have in order to claim the warranty, unless you're able to scalably detect it. That's probably the most important step. And as sites grow, and that process of warranty claiming and becomes very prohibitive. It becomes very expensive unless you can scale it, and you don't want to spend all your time doing a kind of a treasure hunt, having that's not the time where you want your maintenance crew to be. You want you want to be able to pinpoint where the issues are, be able to operate at optimal power output, and to do so in a very economic way. Otherwise solar technology won't be
Right.
viable, won't be able to compete if the labor costs start skyrocketing with the size of
Right.
the facilities. You can think about also, there's during commissioning, you could see this process as kind of a birth certificate for your panels, because you could show from the day the panels were installed, this is how they were, you know, and not and see how they've changed over time. And it helps you because oftentimes we see with this rush of installing panels and rolling things out, things aren't done carefully. There's a lot of in construction, damage that occurs during construction that one can't see, even as simple as you would imagine that walking on panels is quite common by contractors, and there's no way visually to see that damage most of the time. In fact, and it often doesn't show up as a thermal anomaly until many years later. And so you want to be able to capture these things early, so that you could predict beforehand what your maintenance schedule is going to look like, where what your asset, how your asset is going to perform over the years to come. Because if you promise the customers that you're going to deliver, you made that commitment, you're going to deliver certain amount of energy at a certain price. You need to do everything possible to stay on that target. I think there's quite a number. Many people I'm finding as we deal with customers, we're finding creative reasons for why the customers are using it, but that's just a flavor of the two biggest segments.
Uh, yeah, tell us a little bit about, maybe Dilshar, you take this question, or as you see fit, as a team, you guys decide. But tell me a little bit about your customers. What profile companies are they? How do they use the product? What has been the experience so far? How has the product evolved, and what's in the roadmap going forward?
Absolutely. And so initially, right now in the solar space, we can typically divide the solar space into three major sectors. We've got utility solar, where they're obviously focused on providing power back to the grid. And then we've got commercial solar, which is solar installed on rooftops of businesses, whether they be hospitals, schools, etc., where one of the primary focus is obviously providing power to the building, but which is the assets are typically owned by other firms, not necessarily the site they're installed on. And finally, you've got residential solar. When we started this project off, we were specifically focused on utility solar with a goal of expanding to the other sectors over time as we scale up. And utility solar, the biggest challenge is, of course, scale and trying to understand how each company operates, because you've got obviously the EPCs, as Osman alluded to, who are installing the project, and there's a significant chance of damage at the installation phase. Then you've got the site owners, and then you've got the O&Ms. And we were trying to understand what the actual state of solar inspections is. And it varies significantly from the United States to internationally, because technology is extremely variable, but also, for example, solar insurance isn't really as big a thing outside the United States as it is in the United States. And so, for example, we were speaking to a very large power company based out of the Middle East. And for one of their gigawatt sites, basically, practically, they had an O&M who was in charge of maintenance and conducting electroluminescence testing. Now, how were they able to scale it? The simple answer is they weren't. They had 13 people employed whose full-time job was just doing electroluminescence on this facility. As you can imagine, doing that 1 year round, it's just people whose entire job is that. And this is a multi-million dollar budget, nearing tens of millions of dollars annually. So it is expensive. And that was obviously a major insight for us, in that there's an opportunity here to provide a service to be able to make this, to translate this to cost savings for the customer, because this was just imaging. One of the challenges that we've alluded to, we actually spoke to one of the key experts from Europe about EL imaging, and he mentioned that even if he was able to maximize his throughput with manual EL inspections to, let's say, even 1,000 images a day, it would take him another whole day to interpret those images. And that's where software and AI obviously play a very critical role, because there's nothing here around interpretation that AI can't do. And with advanced machine learning models, not only can we identify the types of damage, but we can build classification for potential root cause analysis, or even on the impact of that damage to the bottom line by correlating it to power production, which is actually one of the key advantages of our solution over thermal. Thermal doesn't really give you a correlation between power loss and thermal anomalies. A hotspot doesn't mean you're necessarily producing less power. It is obviously a safety risk that should be resolved. But in the end, there could be tons of panels which are dead. They could have diode failures, etc., but they don't necessarily show any thermal hotspots there. And so it becomes very important to correlate this to something the customer cares about, because fundamentally, solar site owners can monitor production on a string level. They have a lot of data available to them. There's processes such as IV curve testing, where you can test individual panels for their power output. But the challenge in data, in pretty much universally, isn't about the collection of data only. It's about making that data actionable and usable to end customers. And that's why we're focused on a solution as opposed to just collection. Because by making this data usable to an end customer, it actually allows them to see the value of why this data is important. Because if I approach a solar site with a million images of their solar panels, they won't know what to do with them. And while they might be able to tell what a micro crack looks like or a broken cell, if we get into electrical defects like soldering faults, etc., those are pretty difficult to identify for a layman. And that's where making that process simpler is very key. In Europe, we've actually conducted a variety of inspections for the use cases we've alluded to. There was a site over in Switzerland where we were actually called into that site specifically because they had just received a handoff from their EPC. And the site owner had seen the EPC walking on top of panels. And, as Osman alluded, this is a surprisingly common thing. I had a friend who had solar panels installed last year, and his contractor was walking on top of them as well. And
Yeah.
people assume that, well, the panel didn't visibly break, the glass isn't broken, therefore it's going to operate just fine. The glass isn't what to be concerned about. It's the actual underlying silicon. And you can't see that unless you have shortwave infrared. But when you see it, you find very incredible results. Like we found over 20% of the panels on that site exhibited some degree of damage. Now, this damage wasn't necessarily super severe, but number one, it shouldn't have been present. And number two, it allows the site owner to understand one, potentially to get the EPC to make the replacement, or two, to monitor these panels specifically. Because electroluminescence, as Osman alluded, isn't a new technology. In fact, manufacturers already use this heavily. Most panels that you can buy on the market are already inspected using electroluminescence before they're sent out. But they can be damaged during transport. They can be damaged during installation. And this is a surprisingly common thing. It's funny, even
Is
a
one question there to interject, Dilshar, the electroluminescence testing, is that flash testing that they do at the factories before the panels come out, or is that something else
so
that
elect
just the regular thermal imaging drones can also do, or how is
yes.
that different?
So in electroluminescence testing, basically what you need to do is you need to use a shortwave infrared camera. So regular thermal camera cannot do it. And
Okay.
it utilizes an electrical current to stimulate the silicon. Instead, you basically pass a current back through the panel, kind of inverting the flow of how you would normally operate the panel. And under those conditions, the silicon luminesces, and you're able to capture that luminescence using specific wavelengths. And shortwave infrared happens to cover that wavelength, and it allows you to
But
basically
all of this is done at a lab environment.
exactly. So
Right.
traditionally, the thing is,
Yeah.
you can't really do this in the real world. You can do it inside a lab, inside a
Yeah.
manufacturing facility, but the moment you change the environment, it becomes a lot more challenging. And one of the difficulties is, as you mentioned, it has to be moved to a lab. There are
Yeah, that's
actual
a big one.
solar there are actual solar papers where the researchers were conducting electroluminescence testing, and while unmounting and unracking the solar panels and transporting them to the lab, they damaged the solar panels. And
Right.
as you can imagine, if professors who are researchers and trying to do this very carefully are capable of doing that, you can imagine that untrained individuals may cause a lot more damage. And it's the
Yeah.
worst kind of outcome. It's like going to a doctor to inspect your broken finger and they break your finger. So now you definitely know you've got a broken finger, but the doctor caused it. So not really a great solution there. And
Yeah.
that's part of the simplicity of our solution is being able to do it on site. And no, provide minimal disruption to the actual operations of the site because solar site owners, O&Ms, are rightfully concerned about the fact that, hey, if you're taking my panels off site, what, maybe you damage them, etc., are you doing things correctly? And one of the key advantages, however, is that we're speaking the manufacturer's language. We alluded to warranty claims. Manufacturers often have difficulty accepting warranty claims, and they pose pretty high restrictions on thermal warranties or on thermal imaging for warranty claims. We were speaking to a company that does inspections, and they actually mentioned to us that they had done an inspection on a site and they had found some damage with thermal hotspots and a degree of variance that was about 2 degrees Celsius on certain panels, which the manufacturer should accept as a warranty claim. The manufacturer came back with, we want to see 8 degrees Celsius variance here. That is a severe fire risk at that point. And but a manufacturer can do that. But manufacturers utilize shortwave infrared and electroluminescence in their own manufacturing process. So this is something they're familiar with, and it's a very, like, it might be fair to say, like, it's an undeniable truth because if you can see cracks, you can make a claim on those. And the critical aspect, as Osman alluded to, is we're kind of building a lifespan of the entire panel and showing you the lifetime. You might, it might be a bit childish, but you could compare it to, a child's photo album where you've got photos of them as a baby, as a child, as they're growing, and having those photos of the solar panel post installation and over time every year helps you understand how the progression is happening, how degradation is happening, but also what events might cause damage. Because one of the key
Right.
things that impacts solar panels is weather. Weather is a huge factor for this. Um, Back in 2020, I believe it was, or 2022 possibly, there was a Texas solar farm which suffered $500 million in damage from one singular hail event. That's an enormous amount of damage. And hail, particularly in the United States, is a major problem. We actually
Yeah.
had a client over in Belgium who had a solar farm which had been impacted by hail. And they asked us to inspect that. And pretty much all their panels, like, they were covered in cracks. They were so heavily damaged that that site would not be performing at any worthwhile output. And that allows them to file warranty claims, to file insurance claims. But people often get lost in the idea of, oh, well, hail's probably the only thing. But there's so many different types of weather damage that we can identify. And hail is particularly well known just because hail eventually does cause thermal hotspots. So it's what's known in the industry. But wind stress, snow load, and also critically, thermal stress. People have this conception that, the best place to install solar panels is somewhere where it's very hot. Install it somewhere like the Middle East, install it somewhere like North Africa, where, it's a desert-like region. There's going to be a lot of heat. That's great for solar panels. It absolutely is not. Solar panels,
Colorado is the best place, right?
exactly. You want a place where it's sunny, but
Yeah,
not
and
very
cold.
hot because
Yeah,
solar panels operate within a specific range of temperatures, and over 30, 35 degrees Celsius, their performance typically starts degrading. We
yeah.
we actually did an inspection at a carport in the Middle East, which was installed just 6 months ago, and we inspected the panels, and we found that probably about 60% of them started experiencing stress breaks, which is they were warping because of how hot the sun would get during the day. And, you've got the 6-month-old site. Solar panels are typically rated to last 25 years. The economics of solar is very heavily tied to this assumption. And if this assumption breaks, site owners suddenly start losing a lot of money. And it's very critical for them to be able to manage their assets well to ensure that this assumption stays true. because if solar is to remain profitable, it's important to ensure that everyone knows the state of an asset properly. Every other industry, people are monitoring their assets and understand their states completely. And solar is coming around to this notion, but the technology that's been available on the market just isn't sufficient to be able to do that reliably. And that's been the major challenge, and that's what we're looking to address because, you know, it's the equivalent of suddenly going to the doctor, and the only thing, as Osman alluded, that they can do is check your temperature. You know, you're not going to find out about most of your diseases. You're not going to that doctor again. Whereas we're able to essentially provide the equivalent of an X-ray or a
And
CT scan,
uh,
etc.
I think just to add on what Dilsher's saying, like I think there's some people don't realize that there's a dirty little secret in the industry that uh, when I mean manufacturers they rate the panels for 25 years. They didn't actually test them for 25 years. They put them through a series of simulated tests, accelerated heating, in an oven, and maybe UV and under certain conditions, and they say, well, this is certified for 25 years. But in reality, in every environment is different, and a lot of things come at the panel at the same time. You get heat, wind, you get soiling, and all this together. It's not 1 + 1 = 3. It's or 2 + 2 = 4. It's 2 squared plus 2 squared, and you get 8. And so the what we're doing here actually, its long-term effect is going to make the industry a lot more robust, because then and the user, it will benefit the customers in the end, because they'll know really like how long their panels can last in the specific environment. At the moment, there isn't a big enough data. Manufacturers haven't done enough to field work to see how panels degrade in the field over time, because they haven't been able to take the lab to the field. As simple as that.
Right. So
And
you're essentially enabling that with
exactly.
your extreme efficient way of collecting data at much vaster amounts and faster speeds and much less cost. I guess your next challenge is to become the the industry standard by which all of these things are measured to bring truth to the performance level. Uh, because this is like I'm just now doing the math, you know, because in our previous conversation, you guys mentioned, yeah, this is gonna be a $1 trillion problem very soon. And yes, the industry has, you know, 3 to 4 thousand gigawatts now, which is $1 a watt approximately. That is $3 to $4 trillion of assets. Okay, put a 10% yield on that for most solar assets. That's about $300 to $400 billion of cash flow a year. And if there's a 10% underperformance, that is $30 billion. 1% improvement on that is $3 to $4 billion of value creation,
You've hit
or
the nail
value
on the head
capture.
in terms of numbers because right now there are several firms out there, and there's one very notable one who do an annual solar report. And they're working with several firms that utilize thermal. And one of the critical numbers that Osman alluded to as well is the annual known loss for underperformance for solar is already $10 billion. Now, that number sounds impressive, but I want to dial in on one specific word here: known. That is based on thermal and visual inspections. There's a very large unknown loss that we can identify and help resolve as
Right.
well. And as you mentioned, one of the things people don't realize is if you're boosting your production here by 1%, that 1% is essentially pure profit. It's not just revenue because your
Right.
costs are increasing only marginally. And the
Yes.
impact of that 1% is
Your profit
enormous.
goes up by 10% if you do
Exactly.
that 1%. Yeah,
Exactly.
exactly. Yeah.
And the other part of data that's very important here is the economics of solar have one very fundamental challenge in the United States specifically, which is insurance, because insurance is very heavily required in the United States for large-scale solar sites. And
Mhm.
insurance providers are now moving to the point where they're questioning solar a bit, but they continue to want to insure solar. And the reason for wanting to insure solar is renewable energy right now only makes up 10% of energy production in the US at push. And that includes solar and wind. And wind actually right now makes up more than solar.
Mhm.
And fossil fuels makes up the majority of the rest. Yet if we look at insurance claims, 33% of insurance claims are renewable energy, and the remaining are fossil fuels. So why do you insure renewable energy at all? Because by 2035, the total amount of annual premiums for renewable energy, which is largely going to be focused on solar, is going to be $235 billion. To compare that to fossil fuels right now, that's about $22 billion. That's going to be a 10x difference in about a decade on how much more renewable energy companies will pay. Insurance companies see that and they identify they want to continue working with solar. But even in conferences, it's been cited by several experts in the insurance industry that the biggest problem right now that the insurance groups have, they don't have underwriting. They don't understand the assets they're insuring. And so it's kind of guesswork. You might insure an asset, you might do a thermal inspection, but you're kind of just guessing like, oh, sure, this will be fine. And insurance companies don't do that for pretty much anything else. So for companies like them, for warranty claims, for a lot of these processes, having reliable, accurate data is so critical and it transforms the process so much because everyone wants a data-driven process because then there's no arguments about he said, she said about, oh, this is damage or this isn't damage, etc. But when you've got this ground truth, it opens the door for a more profitable industry for everyone because assets that are being well managed will get the benefits of that good management. Assets that are being poorly managed are already seeing a loss and they can understand how to improve and be able to move towards well management. Because right now, solar is profitable, but in the sense of it's the blind leading the blind in a sense, and people are just guessing and saying, oh, well, this will work. And that's fine as long as it works. But
Yeah.
as we're moving on and we're starting to hit 10, 15 years into the lifespan of some of these solar panels, they're suddenly starting to fail. And suddenly alarm bells are ringing. We actually had a lot of sites over in the UK, a lot of installers approach us because they had installed these solar panels and told their customers, oh yeah, these are going to last 25 years. And they had installed these 10, 15 years ago. And suddenly the customers are coming back to them and saying, you told us these are going to last 25 years and I'm not getting the power output I'm supposed to be getting. And they're wondering, well, we don't know how to fix that. We don't know what's going on. And so they're coming to us because we have the expertise to point out to them what's been happening. And that doesn't necessarily mean that their problem will be solved because that's a buildup of a decade of damage. But solar's growth right now is so rapid. We're seeing solar production triple in the US, or sorry, double in the US every 3 years. Internationally, in most countries, it's doubling every 2 years. And that expansion is coming at a cost, but it's also coming at the need for the data around it. Because if suddenly 10 years from now, solar infrastructure starts failing, there's going to be a lot of fallout from that. And we want to be able to avoid that as much as possible.
Yeah. So what, Osman, Omar, you guys have started this journey, and what do you see in the future? Like, what if you could wish anything from the universe? Like, what would you like to play? How would you like things to play out for Q.Fly over the next year, 2, 3 years, so that this becomes a valuable platform for the industry?
Thank you, Kerim. That's a great question. I mean, we are honestly, our roadmap is to reach complete automation. So users would have a system that's really no touch, no interference. All it's basically every has a schedule fly. It flies on its own, does its own, goes
The
back.
drones fly,
Yeah,
alert the robots.
yeah,
Robots change
yeah,
the panels, and the world runs on solar
exactly,
energy.
Well, I
exactly,
mean,
exactly.
the goal is to have a full closed loop system, basically, right? Where you have both like sensors and actuators and stuff. Everything you find triggers an action automatically there. This is kind of like the full vision. It's going to take time to get there, but the first step is to create awareness for this type of technology, because not a lot of people are aware that something like this is a possibility and does exist for most of the people that we're talking to.
Great last words, Omar.
Yeah.
Yeah.
Yeah, when the shampoo came out, most people didn't know that they needed shampoo. So
Right. Exactly. Well, gentlemen, thank you very much for your time. Is there anything else we should mention before we close this conversation? And hopefully we will do more over the coming quarters and years, uh, reporting on your progress and offerings and so forth.
I mean, absolutely. I mean, like I said, this is a very broad topic, and we barely scratched the surface of it in this hour. You know, but you got to start somewhere.
All of that is just appreciate everything you do for solar, Kareem, like the awareness, the insights you provide, and the people you speak to. There's a lot of knowledge we gain from resources such as yours, podcast, basically, to be able to learn more about the industry.
yeah,
It's very invaluable as a resource. Believe me, if we didn't have the ability to hear what experts say, this process that's already taken us several years would have taken us even longer. So, appreciate what you bring to the community, appreciate what Solar Academy does very much.
I, I think as we keep collecting more data, we're going to be encountering very peculiar cases and more kind of unnoticed issues that are billion-dollar issues, and that's where we would love to engage again and talk, share our experience with your audience.
That sounds like a great plan. Again, thank you, gentlemen, for sharing
Thank
your
you,
story and your innovation, and we will do this again. Thanks.
thank you, Karim. Thank you. Take
Thank
care.
you.
Bye bye.
All
Take
right.
care. Bye bye.